When you hear the term terrestrial worlds or terrestrial planets, typically what the subject of that discussion would be are the 4 inner planets and sometimes Earth's moon as well. So this picture from the textbook, you notice that the Earth's moon is included. A couple of reasons for that. The inner solar system really just has these 5 large objects. Mars also has 2 moons, but those are captured asteroids. Those are much smaller than the Earth's moon and smaller than a lot of other moons in the solar system as well. Another reason that the moon is often included, if you just glance at these 2 images here, one from Mercury, one from the moon, they look pretty similar. One big difference with Mercury that you won't notice this on the moon is Mercury has these large cliffs. They almost look like cracks in Mercury or wrinkles at a glance. We'll talk a little bit more about those. Venus is the hottest of the planets, the inner planets, well, and all of the planets. And by the way, inner planets, outer planets, that's another term for terrestrial worlds and Jovian worlds, outer planets. Mercury is closest to the sun, but Venus is actually hotter because of what we would essentially consider a greenhouse gas. It's about 900 degrees Fahrenheit. The surface of Mars would feel like a squishy asphalt parking lot if you were to walk on it. Venus does have volcanoes, similar to Earth and similar to Mars and other objects in the solar system. Venus, if it's geologically active, it's not nearly as geologically active as the Earth, and scientists think that it has a thicker lithosphere, a thicker outer layer. Earth, of course, is geologically active, and as a representative sample of Earth here, it's showing Washington State. So I guess we consider all these other parts here the Washington States of their world. We could sort of consider this the Washington State of Mars, because if you look at this at a glance, it almost looks like a dried riverbed. The main part of the river here, and then it flowed out from here into a delta, so a lower region. When one of the Mars rovers, before it was sent to Mars to practice, they actually sent it to eastern Washington, because eastern Washington, near Moses Lake, Grant County, that has similarities between Mars, or with Mars, because when the ancient lake that was there burst open, it produced a pattern in the land similar to this right here. Here's another view of the terrestrial worlds. Some things to highlight here. One, Earth and Venus are nearly the same size. Just at a glance, their outer surface. They have roughly the same size metal core, roughly the same thickness lithosphere, although since Venus is a little bit smaller, the same thickness for a little bit smaller means it's a greater percentage of its size. The mantle, or the crust, sorry, we'll get it right the third time. The metal core is a little bit smaller, proportional to the metal core of the Earth compared to the whole Earth. Mars has a smaller metal core. The moon has a much smaller metal core, and the thing that's labeled as the lithosphere in those, the so-called outer layer, is much thicker. So the soft, malleable part here of these planets, Venus and Earth, large, soft, malleable part. Mars, not much at all, very small. And the same with the moon, and especially with Mercury. One thing that really stands out, Mercury has a very large metal core compared to its size. So much more than half of the diameter of Mercury is its metal core. As with other things, with planets, size matters. So if we compare a small terrestrial planet with a large one, so a small planet is going to cool quicker, just like you get a hot food, you take bread out of the oven and you cut off a piece and you take it and man, it's too hot, so you break it up into smaller pieces. Smaller pieces have a larger surface area to volume ratio, so it cools off quicker. So these planets have cooled, which means the mantle here is not as malleable, which means that there is not going to be plate tectonic activity, which means no earthquakes, but also no volcanoes. No volcanoes means no outgassing, so nothing to add significantly to the atmosphere. Because it's small, it has a weak gravity, which means it's going to lose, much more likely to lose, any atmosphere that it does have. And also because it doesn't have a liquid core, it's cooled off, and cooled liquids become solid. Small terrestrial planets also don't have magnetic fields, so the solar wind is going to interact with those atmospheres more and blow them away. Large terrestrial planets, such as Earth and Venus, has a mantle with convection, which means that there is tectonic activity, which means volcanoes. So the atmosphere that it had to begin with, represented by the blue, and the addition to the atmosphere represented by the outgassing from volcanoes, is less likely to be lost because there's a liquid metal portion here near the core. It's going to have a magnetic field, which means that it's going to be protected from the solar wind, which means that the atmosphere is less likely to be blown away. So a lot of things work together to make small terrestrial planets not have an atmosphere and not be geologically active. Things work together for the larger planets such that they do have an atmosphere and they are geologically active. Distance also matters. So planets that are closer to the sun, they're going to be warmer, and warmer particles, so as the temperature goes up, particles that are bouncing around like that are going to move faster, and the faster they move, the more likely they're going to shoot off and be lost from the gravitational attraction of that planet. And because they have no atmosphere, and because the liquid, water for example, would have evaporated off, so no atmosphere, no water, so no erosion, so the craters that are there are going to stick around, similar to Mercury and the Moon. And Mars is sort of in between, being a small and a large terrestrial planet. Planets that are far from the Sun, they do have an atmosphere, but they're cooler, and their atmosphere is more likely, or a larger percentage of it, is going to condense into ice. So there's going to be less liquid in the atmosphere. It's because part of the atmosphere is condensed out. It's going to have a more diffuse atmosphere, and because it's too cold for liquid water for sure, it's going to have less erosion. Not quite as minimal of erosion as a smaller, closer planet, but less erosion, so craters are still going to be visible. So with here, you can sort of see the comparison. Lots of craters for Mercury and the Moon, some craters for Mars, very few observable craters on Earth and Venus. Back to this ridge here on Mercury. As Mercury cooled, because even though it's close to the sun, at one time it was hotter, and the core radiates off its heat, so it cools, and as it cooled, its core shrunk. Well, the inner part shrunk, and the core isn't as malleable, so when it shrunk, it got these cracks in it. So it's kind of like if you took a balloon, blew up a balloon, wrapped it with aluminum foil, you could make that aluminum foil look pretty smooth. But if you poke the balloon, the aluminum foil is going to look more wrinkly. Not the greatest analogy, but same sort of thing here with Mercury. And this is showing these cracks as being gigantic. Remember, as with George Costanza, shrinkage not to scale. Venus has what we would consider a runaway greenhouse effect. Part of that is due, Venus is sometimes called Earth's twin because it's about the same size, but it's a lot closer to the sun. So if we could move Earth closer to the sun, Superman, instead of doing something to the rotation, decides to move Earth closer to the sun. So these little wiggly lines represent solar radiation. There would be more solar radiation, which means the atmosphere would heat up, and the surface would heat up as well, as would the water would heat up. So that would be more water evaporation because the atmosphere is warmer. Warmer air can hold more water, So that means a lot more water in the atmosphere, which means a lot more precipitation. Less water on the surface and more water in the atmosphere means that the carbon is going to move out of the rocks, leach out of the rocks, and there's going to be less carbon in the rocks and more carbon in terms of carbon dioxide in the atmosphere. The water vapor, the increased water vapor is a greenhouse gas. Increased carbon dioxide is a greenhouse gas, so that's going to keep radiation. So this little squiggly line here is showing radiation coming in, but radiation radiates off the Earth. I need a better vocabulary, don't I? So in the daytime, sunlight comes in, hits the Earth. At night, most of that radiates out into space. If there was a thicker atmosphere and a shield of water vapor and carbon dioxide, that radiation is not going to be effectively lost into space, making the surface warmer and the atmosphere warmer and resulting in a Venus-like greenhouse effect. Here are 3 images from Mars. One is actually a computer simulation because it shows water that isn't there right now. But there are a lot of characteristics of Mars that show that at one time it was wet. One of them is Mars has a fair number of larger craters, but not nearly as many smaller craters. So again, we look at Venus. We look at Mercury, and we can see some pretty tiny craters. We can see smaller craters within craters. Here's a big crater, and then a medium crater, and then some smaller craters near it. You don't see that as much as on Mars, which implies that there is erosion at work on Mars throughout its history, certainly in the past. You've got patterns where you've got uplands that are relatively flat. You've got these crevices that lead down to lower indentations. Certainly looks like a larger body of water flowed down and filled up a lake, similar to things that we would observe here on Earth. And like the picture I showed you before, the appearance of dried riverbeds and river deltas as well. So even though Mars does not have significant amount of flowing water now, if you read some books, even our textbook I think says Mars has no liquid water on the surface. Now astronomers are thinking that there might be times of year where there would be a little bit of liquid water flowing on the Martian surface during the warmest time of the year, but it evaporates out very quickly because of Mars' thin atmosphere. And that, kind people, are the terrestrial worlds.